Good morning, everyone. So welcome to the third day of the school. So today we are going to have the second lecture of Misha, then after that the first one of Glaucia, and the second one by Stefan and Steve in the afternoon. We are also going to have a panel discussion, a round table, so more announcements on that later. There is going to be some cachaça involved, so and okay, so also like the second poster session later on. Today we follow cocktails. I'm sorry for that, but the budget is limited. Yeah, so Richard, many thanks, and the stage is yours.
Hi. Okay. Yeah. Welcome back. I really appreciate that so many of you managed to get up early for this lecture, despite having cocktails yesterday. I know it's hard. I really appreciate it. So today we will take the second step of our journey towards more efficient data processing techniques that hopefully help us to really enter the quantum realm with large quantum computing architectures. The setup for today, like I have 3 lectures in total. And last time, we looked at measurement design when we already know certain observables we want to predict. So we started with observables and then tried to come up with estimation strategies. Today, I want to shift perspective and look at state approximations instead. Kind of like similar mindsets, but now we want to get efficient state approximations of an unknown quantum system. And here is kind of like the outline for today. I will start with the recapitulation, remind us all what we did last time, and then start from there to kind of like develop a randomized measurement strategy in a similar spirit to Monday that will help us to get classical descriptions of quantum systems. And research doesn't always work in a linear fashion. Maybe this is something you've already noticed. I notice it every day. But sometimes failure even tells you something new and something to learn. And I want to emulate this here by starting with an attempt of a randomized measurement protocol that will fail. And we will see why it fails, and we will fail with grace and kind of like make it better, and then make a second attempt, and I promise you that the second attempt will succeed. And this promise will come in a strong way because we will prove rigorous, efficient convergence guarantees again that gives us credence, really mathematical credence, that these ideas can work. And then to close today's session, I want to really go to a field test and show you how these ideas actually work on a real quantum computer, in our case, a trapped ion computer. So kind of like this is not only mathematical mambo jumbo, but it works in practice, and I'm very excited to show you that. And then, as usual, I will stop with homeworks for those of you who are really motivated. And today I decided to also give you some pointers towards literature, if you maybe want to read a bit more on the topic, and because I think this is very, very important, also suggestions for markdowns. These are coding tutorials that show you how you can code these ideas by yourself on your classical computers and really play around. Okay? So here, I want to start the recapitulation with really the big vision that keeps me going and that kind of like drives this field. And it's written here. We set out to learn many things of a large quantum system in a tractable, scalable, and trustworthy fashion. And each word here is important. I really want to be able to learn many different things, and maybe I don't even know in advance what I want to learn, but I kind of like want to learn a lot about the quantum realm. And I want to do that for a large quantum system. Like think about kind of like the quantum computers that Fernando is building, or that IBM and Google have. And I have standards for that. I want our approaches to be tractable in the sense that we can execute them today. So I don't want to have to rely on fault tolerance and quantum error correction. I want to have a solution that works today. I want a scalable solution. I don't want to wait for the rest of the lifetime of the universe until my data processing is done. So this is important. And the last thing is I also want it to be trustworthy. I want to give you arguments that these ideas can work. And these will always be mathematical in nature and are always a bit pessimistic, but they overall show that these ideas work. And it's not just something I cooked up over cachaça. Last time we did such kind of like an exploration of this big vision on a quantum architecture that looks a bit like this. And I emphasized the task of estimating observables, in the simplest case, Pauli observables. So here's a concrete example that was also in the homework. This is a Heisenberg Hamiltonian on n qubits. And if you count, it has roughly 3 times the number of qubits many terms, some xx, some y, some zz terms. And the natural question actually is, can we learn all these terms as efficiently as possible? And then we looked at 3 strategies, if you remember. There's the sequential strategy, which I wouldn't write it on a slide, but I would call it the stupid strategy. You can start measuring the first xx term, often enough to get good convergence, to get a good idea, and then you can measure the first yy term, measure the first zz term, and this is fine, because they're incompatible, but the sequential way tells you that in order to measure the second xx term, I start a new experiment and collect new data. And this is kind of like where the normal optimality comes from, and you can easily convince yourself that the number of shots you need is linear in the number of observables. And note, this is like some learning curve of myself. I've written capital M for the number of shots. Last lecture, I chose capital T here, which was an honest computer scientist's mistake. Thank you for making me aware of this. What was T before is M today to avoid confusions with time. And just to emphasize, this M doesn't mean mass or anything, it's really just an image. I hope this is better than my first attempt. And then, for this type of Hamiltonian, it's actually also not so difficult to come up with an optimal strategy. And I guess many of you see that already, and those who did the homework kind of like realize that for sure themselves, that these 3 terms are incompatible by themselves, but we can jointly measure all the x terms, and we can jointly measure all the y terms, and we can jointly measure all the z terms, because these 3 groups are compatible with each other. So in this case, the optimal grouping problem, group your observables into collections that you can jointly measure, is very easy. And you can group them into, well, 3 groups. One where we only do x measurements, one where we do only y measurements, and one where we do only z measurements. And if we do that, that's really the optimal solution. It's possible because this Hamiltonian is very easy. Then you get a number of shots that is 3, the number of groups I have to do, and times this log over epsilon squared factor that ensures that we can use the same shot data for all different observables within one group. So if we do that, we improve L, the L dependence in the sequential strategy, to 3 times log L, which is an exponential improvement. And the last strategy, and this is the one I'm going to focus on here, is the randomized strategy. This is where we did our denial of service, and we didn't even try to do a grouping problem, but in each shot that we take, we choose these unitaries randomly to rotate us either nothing at all, then we do a z basis measurement, into the x basis or into the y basis. These are 3 possible rotations, and for each shot we choose them uniformly at random. And then we basically play the lottery, and probability theory tells us that for each of these terms, the probability of getting a good compatible measurement is 1 over 3, because we have to hit the first qubit, times 1 over 3, we have to hit the second qubit. That's an overhead of 9 that we have to pay, and this is why we get a 3 squared cube. And otherwise, we again get this log dependence on the number of shots. So kind of like scaling-wise, the randomized strategy is almost the same as the optimal strategy in this regard. You pay an extra factor of 3. But here, you have to think. Admittedly, you don't have to think hard because this is an easy Hamiltonian, but here you don't have to think at all. And the automatical post-processing does it for you. And you can see that kind of like this idea was very much driven by observables that we're interested in. And then we have the state, and we didn't care so much about the state. And today, I want to shift focus and forget the observables for now, and really think about the quantum system and whether I can use similar ideas to get an efficient classical representation of this quantum system that I can afterwards use to predict observables. So we start with the state and not the observables. Okay? And here is the high-level vision if you want to set out, that we had when we set out to try to come up with scalable, tractable, and trustworthy state approximation techniques. The setting is, again, think a large quantum system. We will assume that it's n qubits, really like a quantum computer. And then you can immediately see that the associated wave function has 2 to the n degrees of freedom, right? So this is a huge number. If you have 10 qubits, it's 1024. That's kind of like not so big yet. But if you have 100 qubits, kind of like it's probably like the number of degrees of freedom is larger than all the atoms in Paraty. And so these are really big problems. And the standard techniques that you would use, maybe you've heard about quantum state tomography, they would scale in this exponential dimension. So it's really impossible, like inconceivable, to do full quantum state tomography on a 100 qubit system. Okay, and so we need new ideas. And what we did is we really took the point of view of such a quantum architecture, a device that allows us to prepare a state, then apply some simple gates, and then measure in the end. This is kind of like a setup that we looked at it last time. And some of these devices don't struggle. They don't see this exponential overhead. They can prepare interesting quantum systems, and you can measure them in real time. So some of them work a bit differently, right? And like if we build them, this is one of the reasons why we built them. They are really good at preparing these complicated systems, and because they work in the quantum realm themselves, they don't necessarily see this complexity of having 2 to the n amplitudes. This is something they natively explore. And so the quantum devices actually allow us to prepare interesting quantum systems that maybe allow us to peek into the quantum realm, like either by solving an algorithm or maybe like simulating a quantum mechanical process, or just being curious and trying to explore the world of qubit systems. And an interesting feature that people usually complain about is that we cannot access the associated density matrices or wave functions directly. This is something you quickly learn when you work with quantum architectures. It's not like a quantum mechanics class. You don't write down a wave function, you cannot simply access it. It's impossible to ask the quantum computer what is the 10,304th amplitude of U. It doesn't work that way. Instead, you can prepare it, and then you have to measure it. And you will always get these bit strings as outcome, and they are probabilistic in the single shot limit, and also disruptive. They typically strongly interfere with the system in question, and if you do, in 3 cases, optics, like if Steve does a measurement, I guess he destroys the photon, and the quantum system is really gone. And so you really have to start from scratch again, prepare a new copy, and then measure. But what quantum devices allow us is to sample outcome distributions where the probability depends on the quantum system. And this is subtly different from having random access to all the amplitudes. This is what a classical computer would do. And typically, and maybe you are with me if you did experiments in some theory, this is typically an annoying feature. Like many of us, myself included until 3 years ago, thought in terms of density matrices and expectation values, and then it was always a pain in the ass to get enough statistics to get a good description of the system to then compute the expectation values. This is just not how quantum systems work. And traditionally this is viewed as a curse. Experiments are expensive because we have to do them often. But we think that this is actually a blessing and not a curse, because it is an interesting effect that would be difficult to simulate classically. Okay? So kind of like instead of being annoyed by the sampling approach, let's try to view it in a positive light. And how is this possible? We want to use this ability to sample from different distributions to empower one of the most successful simulation and data processing strategies that we have, which is Monte Carlo approximations. I'm sure all of you have seen Monte Carlo as a technique in one way or another. Maybe you've seen how to use random function evaluations to approximate an integral. Right? This is something that physicists like to do. Or, one of my favorite examples of a Monte Carlo technique is to approximate the value of pi. I'm not very good in algebra. It's a really nasty number, but I really like tossing coins. And maybe you know this example, but one way of kind of like approximating or computing pi is to try to compute the area of a quarter circle like this. Because you know exactly this is equivalent, if you were to compute this area, would be equivalent, I think, to pi fourth if the radius is 1. Now, I don't know what pi is. It's an irrational number. But what I can do is I can toss coins on a tile that looks like this. Just randomly drop points. And then once I drop such a point with a uniform distribution here and a uniform distribution here, it's easy for me to compute whether it falls within the surface area or outside. I just compute its Euclidean length. Okay? So this is also easy. I sample two random numbers, build a two-dimensional vector, and then I check whether the length of this vector is greater or equal to 1 or smaller or equal to 1. And if it's smaller or equal to 1, it's inside my circle, and I say this outcome is 1. And if it falls outside, I say my estimate is 0. Now what happens if I average this over many different trials? I will approximate the area, right? And I will do that in a completely simple way. All I need is a random point in 2 dimensions and the ability to compute and add squared length. This is orders of magnitude easier than any algebraic approach to compute pi. And you can prove that it works and that it actually converges. So this, in a nutshell, is the idea of Monte Carlo. Start with a probabilistic process that gives you simple things that you can efficiently compute, and you know that if you were to form the expectation value of many such trials, you would get the complicated answer you're interested in. Pi over 4 in this case. And then you keep on going. And this idea is not only useful for computing pi, admittedly, it's a very bad approach when you compare it like to the ideas that Ramanujan had, but it is still a very, very powerful technique that is also popular in big data analysis. I don't know if you know that, but kind of like in big data analysis, in reasoning, and like if you look at really, really large problems, like for example, understanding ocean currents, then the matrices of the data you get become so huge that you can't fit it into one computer. And then even the simplest routines become very, very difficult. And so what people do there is something very, very similar. You take a large, complicated object. This could be kind of like time series of all temperatures in the Atlantic Ocean, or it could be a quantum system. And you try to approximate it as an expectation value of much simpler guys. Think of very, very sparse vectors, if you want to do like, let's say, a streaming analysis of ocean temperatures, or think about uncorrelated systems if this were a quantum system. And if you manage to write down a formula that approximates this complicated object as a probabilistic average of simple guys, this opens the gate to Monte Carlo approximation in the same way as here. I just have to find a way to generate a random sample, and then it is simple, and I can process it. And then I do this over and over again, and just average. Okay? And for those of you who have worked with Monte Carlo, for those of you who have paid close attention to what I just said, why isn't everybody using Monte Carlo all the time? What is the computational formula in such approaches?
Big number of shots.
Well, yes, There's this curve of Monte Carlo of 1 over epsilon squared, very good. I would argue that in a quantum setting, this is actually not a problem because we have this short noise regardless of what we do, because we don't have direct access, but you're right. We need a large number of shots to get good accuracy. But suppose this is unavoidable, which for us it will be. What is the other big part? When you were to code a Monte Carlo approximation, where do you sweat?
Sampling randomly?
Yes. You need to have a way of sampling according to the right distribution, which can be complicated. I mean, here already is the hardest part because you have to sample a uniform random variable in this direction and a uniform random variable in this direction. This is doable, but it's like the hardest part in this approach. Here, I hope you believe me, that it's much more difficult to find a probability distribution such that this is equal without actually computing it, because you can't afford that, and then sample from it. So this is the real problem in Monte Carlo. Okay? And this is one of the reasons why Monte Carlo is still being used, but not the go-to strategy when you want to approximate very, very big systems. Okay? It's the bottleneck. But maybe in quantum computing, this is not the case. I want to remind you about this fundamental feature of quantum technologies. We can't access raw directly, but we can sample from distributions that represent it. Okay? This is what a quantum computer or quantum architecture does natively. And as it turns out, this exactly closes the hole of the biggest issue with Monte Carlo. We can just outsource the hardest part of the Monte Carlo approximation, the sampling part, to a quantum device where it does it natively. And then do Monte Carlo on the classical side, because now everything is easy, to make sure that we have scalable approximations that we can compute and store. Because this is what Monte Carlo gives you once you know how to sample. This is the main vision of the randomized measurement toolbox. And the idea is that in the data acquisition phase, we use randomized single qubit measurements, we will see more later on how that works, to create simple random matrices, uncorrelated density operators you can think of, that approximate the true underlying quantum system in expectation if I average over all degrees of freedom for every possible quantum system. And once we have such a setup, and the quantum computer will do that for us, we can use Monte Carlo averaging, much like in the approximation of time before, to compute and predict many features of the state in parallel and computationally efficiently. So it takes the best from the quantum measurement problem, which in this case is a quantum measurement solution, and classical Monte Carlo techniques. And as a gimmick, if you do that, the data acquisition phase, your randomized measurements, and the things you want to predict in the Monte Carlo fashion become completely uncorrelated. It's really, the motto is measure first, ask questions later. Are there questions or comments at this point? I think this is conceptually the most important slide of my lecture. And I really hope that I could convey the main ideas of a fruitful synergy between quantum architectures and sampling on the one hand side, and classical scalable Monte Carlo on the other side. And I really hope that you can see on a high level already that these two go together nicely. Are there maybe comments or questions from your side, or maybe just reformulations, because this is really the main message of the entire randomized measurement toolbox. Great.
Can you just re-explain the item 1? Just because I didn't get that completely.
Oh, no, this is just a high level idea. We will prove it now, and we will fail at it. This is just the overall strategy.
Okay, so I think I got lost in this because since you said that this is the most important
Yes.
idea, I don't think I get it completely.
If I give you a quantum computer, what would the quantum computer do for you? Let's do a discussion.
I don't know, certain tasks are better realized on a computer than
Well,
on a computer.
That's the Polish businessman's answer, right?
Yeah.
It allows you to prepare states, maybe states you care about, and then you can measure the individual qubits to learn something about the system. This could be a solution to a quantum computing problem, but more fundamentally, it allows you to explore the quantum realm. Okay? Are you with me?
Yeah.
And now, suppose you want to learn things about the underlying quantum system you prepared. If you don't want to do that, you wouldn't need a quantum computer, right? Then how would you do that? You would prepare the system, and then you would measure it. And Bohr's rule tells you that the outcomes are random, and a single outcome doesn't contain any information about the quantum system. All the information is hidden within the probability distribution. Okay? Are we on the same page?
Yeah.
And then traditionally this is viewed as a bad thing because we want to learn the distributions and then we have to create many samples in order to approximate. And what I'm saying here is this is good because the process of being able to generate these random bit strings in a fashion that all information about the system is encoded in the distribution is exactly the same as we had kind of like in this Monte Carlo example, where we have a distribution of points that lie within the circle. And so we can really use this as an auxiliary routine to empower well-known and very successful classical techniques that use precisely this. Was this helpful?
Yeah. Thank you.
Hi. I think that I would like a little, because I did study Monte Carlo like a long time ago, but I don't really remember how it works in the classical computer. So how is I know that we can't sample completely randomly in a classical computer, and I can understand why having an actual quantum state that we're sampling from would guarantee that it's random, and then the data would not be coupled. But how would it be coupled? Like, I would like to. Could you contrast to how this would be in a classical computer? What is the relation that they could have?
Well, in a classical computer, you normally assume that you have randomness, and typically you use pseudo-randomness, but with a good hashing function, and this is good enough. Mm-hmm. And so kind of like in a classical computer, you write down your own algorithm, which is the most complicated part, where you take pseudo-random bits and somehow convert them into the randomness that would resemble a probability distribution that solves your problem. Mm-hmm. Okay, right, like in this case, I would use two uniformly pseudo-random bits to create a two-dimensional random vector, where I then evaluate the squared length in order to get an estimator for the area of the circle. Mm-hmm. Okay, and kind of like if you go to big data, the overall approach is similar, but it's always the same. You use pseudo-randomness, external pseudo-randomness as a resource, and then you reshuffle it in order to resemble a probability distribution of something more complicated. And then you would sample from that.
Mm-hmm. Yeah. So what exactly is the disadvantage of a pseudo-random? Why is it not good enough, basically?
Because the algorithm you write, if the matrix has 10 billion rows, requires 10 billion random bits, and a runtime that is also 10 billion, it's really scaling.
I understand.
Whereas if you have a quantum computer with 100 qubits, the number of degrees of freedom and the number of bit streams you can get is way larger than 10 billion, but it does it natively in the blink of an eye.
I understand. That's very cool. Thank you.
Thanks. I think this was very helpful. And it's not fundamentally difficult. Let me re-emphasize this. It's not about pure randomness and like a fundamental difficulty. It's the difficulty of scaling it up and still seeing a solution in your lifetime. Thank you to both of you. I think this was really helpful and cool.
Now the message of our advertising.
We'll be back after the commercial break. Okay, so let's try to cook up our Monte Carlo strategy to overcome precisely these scaling issues and use the fact that quantum computers with 100 qubits still give us random bit strings in the blink of an eye. Even if we were to want to simulate it classically, we would never have the chance. Okay? And let us start with an attempt that will fail, but it's simpler and it conveys the main ideas. So here, again, let's look at a single qubit first, understand the base case, and then scale up to many qubits, because this will be easy. Here is an unknown quantum system, single qubit now, black box row, and I just perform computational basis measurements. And then I can get an outcome 0, or I can get an outcome 1. And this is a random outcome now, but the underlying distribution depends on the unknown quantum system. And now I want to use this as a random number generator that allows me to approximate features of rho, like in a Monte Carlo setting, but this is now very easy, it's a single qubit device. And here's the most naive idea you can think of for a Monte Carlo approximation, is suppose you perform a measurement and you get outcome 0. Well, then I can simply say that my estimator approximation for the unknown quantum system is 0, because this is what I've just seen. It's kind of like I do a measurement and then I say, okay, my best guess for the quantum system is the measurement outcome I obtained. And this will be correct if my quantum state were actually the 0 state, because then I would have always measured it. But I also do that because the computational 0 state is easy and simple to work with, which is important for Monte Carlo, right? And now, following up on this idea, what do I do if I see 1? Well, I maybe say, my Monte Carlo approximation for the quantum state is the computational basis 1 state. Also the post-measurement state, if you think about it. Okay, this is like an easy strategy of the classical Monte Carlo method. These are classical approximations of the quantum system that uses a quantum device to generate the randomness necessary. And it's as simple as it can get. Now, maybe it's good enough, and maybe not. What happens if you are really for Monte Carlo approximations here? Then you can really visualize this in a blob-sphere equatorial picture. You only have like the computational basis. And let's assume that our unknown state is maybe somewhere here. Okay? And remember, I do a Monte Carlo approximation by measuring the system in 0 or 1. And if it's 0, I say, this is the state. And if it's 1, I say, this is the state. And now if I do this many, many times to compute the expectation value, you will see that this Monte Carlo average will converge to this point, which is not completely bad, because it's much closer in this line to rho than on the other side. And this uses the fact that 0 is more likely to occur than 1 if our state is closer to 0, right? But is this a good Monte Carlo estimator? No, right? It really doesn't point in the right direction. And so if you actually do the mathematical computation, you see that in the limit of infinitely many Monte Carlo samples, I compute the expectation value of this matrix, and this is just the diagonal entries of rho. This is what you see here. It's a projection of rho on the diagonal plane. And this shouldn't be surprising for you, because in our measurements, we only ever did computational basis measurements, and so we only ever addressed the diagonal. So this approach kind of like checks almost all the boxes, but it doesn't give us the right answer for Monte Carlo, because we are blind towards off-diagonal entries. Okay, and I think this makes sense, right? But otherwise, it's a great start. But still, we failed. This is not a valid Monte Carlo approximation, because our estimators don't converge to the true quantum system. So let's learn from this mistake and do it better. Second attempt. Well, we now understand why our first approach failed. We only ever measured in one basis and had no chance of accessing off-diagonal entries. So let's change that by looking at different bases. Okay? Maybe the computational basis is a good idea, maybe the X basis is another good idea, and maybe the Y basis is a third good idea, because they form a set of mutually unbiased bases. And it allows you to really explore all directions in quantum space, right? So this is now a bit more complicated. I still do a 0-1 measurement, but now I insert a basis transformation detail. And in the spirit of Monte Carlo, we want to get very random answers, so it makes sense to also choose this unitary randomly. So to maybe even inject a bit of classical randomness in order to empower this randomized sampling strategy with additional randomness to get something richer. Okay? So now the strategy is almost the same as before. I prepare my state, then I use classical randomness to decide whether I measure the egg in the z basis here, or I rotate to the x basis, or I rotate to the y basis. I need kind of like a dice or something for that. And then I measure. And now, what would a reasonable Monte Carlo approximation be in this regard? Well, if I see 0, I could do the same trick as before. It wasn't so bad. I say it's the computational 0 state. But now I have to keep in mind that I might have rotated my basis before, and this is not the computational basis anymore. So I take this into account by applying the adjoint unitary to this state, which basically just goes into the basis that you've measured. Looks mathematically complicated, but what this says is if we measure the x basis and you see plus, then this is the plus state. And if you measure minus, this is the minus state. Okay? Not same spirit as before, but now we take into account that off diagonals exist and we rotate into them with a certain probability. Now what is the expected behavior of this? Here is a proof by picture if we do these Pauli basis rotations, identity Hadamard or S times Hadamard uniformly. Same picture as before, I ignore the y-axis because I don't want to draw in 3 dimensions. Same state as before, but now we either measure in 0, 1 or in plus minus. This is basically what the setup says, and you do both of them with the same probability. Now if you do this many times, what do you get? You get something that looks like this. And I hope you can see that. Because with probability 1/2, I measure here, I would get the projection onto this axis. If I measure here many times, I would get the projection on this axis. And then because I do these and these with the same probability, I would average these 2 possibilities to get the point in the middle. Okay? And as you can see, this now looks much more hopeful than before, right? Because it points in the right direction. We just shrunk it and put it further into the maximally unique state. But we know the direction. And if you kind of like do the proper computation, and this is the most central identity in my entire lecture, you can compute that this process leads to an effective depolarizing effect of the underlying quantum system. It's like applying a depolarizing channel with a certain survival probability to it. And in the block picture you see that you're pulled inside. Okay? I gave you a visual proof, but one of the homeworks is to really just compute this. Because you can do that, there's not so many things to sum up. Okay? So, our classical Monte Carlo approximations are on the right track. They're easy to store, they're easy to manipulate, but if I average them, they kind of like are shrink into the drop state. What do I do? Well, I just undo the depolarization effect in the classical post-processing. Maybe you've heard that you cannot invert quantum channels physically, but I don't care. This is now just a Monte Carlo approximation on my computer. And I know how to invert a depolarizing channel on my computer. It's not a physical operation, but I couldn't care less. I just want something that gives me the true state if I form an expectation value. Because then I'm done and I can do Monte Carlo. Okay? Yes?
If you have, after your measurements, you have like, that you start with a pure state. So
I don't know that I started with
pure state.
I never want to know that.
Alright, because if you know that you have a pure state,
yes.
Like wouldn't you just be able to, like, if you know, is in the same line of the as a vector, just changing for a mixed pure state, so could you just use like an extension of it?
Yes, of course. And you're being very smart. Can you do the same for 100 qubit states?
No.
On your computer? See? We will be able to do this. So kind of like I'm being stupid on purpose here, because this will allow me to scale up. And I fully agree with you that this is not a good solution in single qubit sector. But if you bear with me, you will see that this solution generalizes to thousands of qubits, and every smart solution I know does. Okay, thank you, excellent point. Well, I hope you're not very surprised that the mathematical inverse of the depolarizing channel applied to our estimator is 3 times the original state minus the identity. Kind of like a blow it up again, and then I have to like subtract something to take care of this stuff. Okay? So this is really the mathematical operation that takes this guy and pushes him out again to really represent the original state. This is a random matrix now, because we use, this has been a randomly selected unitary, and this is the bit that we got from a random quantum measurement. And this is a pure state, this is the maximum mixed state, we have a minus state side, and a factor 3. So this random matrix is unphysical. In quantum mechanics, people tell you do not do that, because the largest eigenvalue is 2, and the smallest eigenvalue is minus 1. But these unphysical guys are simple to write down and obey the Monte Carlo condition. So if I average it, very, very often I will converge to something physical. It's just that each specimen is not physical. Okay, so this is the price we'll pay. And this is where we're really doing something stupid in this setting. But here's the reason why I still think it might be a good idea. We can now take the intuition we got from a single qubit case and blow it up to as many qubits as we want. And now we just do, for each qubit, we do the operation we did before independently, in parallel, and to get an approximation of the full n-qubit system, we form the formal tensor product of these single qubit estimators. And those of you who have worked with correlations can immediately see that this is a completely uncorrelated system. It's really an elementary tensor product, everything factorizes. So this is really something I can store efficiently and I can process efficiently. This has not many degrees of freedom. And the beauty of linearity of quantum mechanics tells you that this big collection of n different tensor products approaches the true underlying quantum system, regardless of how complicated and correlated it is, in the limit of infinitely many repetitions. Why? Because we've shown that all of these single qubit things do the right thing. And they do it independently from each other. And I can write a highly correlated density matrix as a formal sum of tensor products. This is what linearity of quantum computing tells us. And this linearity just tells us if this works for any tensor product, it also has to work for linear combinations, and so you really get any possible quantum system here. And this is the reason why I chose to do something stupid in the single qubit case to get something scalable here. Okay? And let me re-emphasize this. Each of these guys that we produce with classical and quantum randomness is an elementary tensor product. So it's cheap to write down and it's cheap to process. But it gives you the right expectation value as well. And the price you pay is that you're completely unphysical. Because each of these elementary guys has a negative eigenvalue. A saving grace is that each of these guys, if you take the trace is 1. So it's a bit like a density matrix. But if you really compute the eigenvectors of these guys, you will be scared, because the largest eigenvalue is 2 to the n, and the smallest eigenvalue is minus 2 to the n minus 1. So these are really grossly unphysical objects, but they have a very, very good tensor product structure, and they approximate any physical object if I take enough Monte Carlo samples. So this is how we generate data in randomized measurements. Okay? Now, let's move on to prediction. Yes?
maybe stupid, but just to visualize, because for the single qubit case, you had a block sphere, and then
Yes.
you were
Yes.
basically estimating
Yes.
one point inside it, but now it would be like this row that you are getting is a string of several entries, where
yes.
each of them is one of the elements of the matrix.
No, this is kind of like really like a product state, like a mixed product state. A tensor product of density matrices, with the caveat that each guy in the tensor product is not a physical density matrix because it has negative eigenvalues.
Yeah, so I mean the ending thing that you are estimating,
Yes.
the row, the
Yes.
initial and qubit state, in this case is written as a vector, and each entry of this vector is one element of the matrix.
No, I'm not following. This is just kind of like an underlying physical object that I could store as a 2 to the n by 2 to the n density matrix, but I can afford it, but it can be any quantum system. But I just proved to you that I can rewrite a dense density matrix approximation as a probabilistic average of such uncorrelated tensor products. It's a bit like kind of like maybe you know the theorem of separable states and dependent states. Now I allow for negative eigenvalues, and if you allow for negative eigenvalues, you can write down every state as a probabilistic average of unphysical tensor products.
Okay.
Issue. So in the single qubit case, you had to undepolarize,
Yes.
right? And here, how you undepolarize?
I did?
So you do it like on each
Yes.
single system.
Yes.
Okay.
Because kind of like here we only do single qubit operations, so we don't correlate. And the measurement breaks all correlations anyway.
Perfect.
So I would get a tensor product as a post-measurement state, and then I depolarize this qubit by qubit,
Perfect.
which respects this tensor product structure.
Hi, thanks. I just want to make a comment. When you do tomography,
Yes.
you almost always have some measurement results that
Yes.
are unphysical, and then you have to do some sort of maximum likelihood.
Yes.
So, I mean, I'm not scared at all by the fact that you have an unphysical row which you can average. So, I think here it's really nice because you have at least some, let's say, a fundamental way of getting to the physical row. So.
Awesome, thanks. I really appreciate the support from the expert. Yes.
So this may be a bit unrelated, but what you do for the first qubit case is basically like in a way to write your state as a linear combination of an over complete basis.
Yes.
So it is very similar in a way to the frame approach to quantum information, right? When you choose a frame for the space of operators, and then you define some kind of overcompleted function for your operator, and you estimate.
Yes.
Would you say that this, what you're doing here, is like a kind of approximation of a quasi-probability distribution for frames, but without the negative signs, because it's just summing the...
Well, let me answer it the following way. I did my PhD on frame theory. So these ideas are deeply rooted in frame theory.
Okay.
And in the end, I don't want to talk about quasi-probabilities or something like this. I really try to find a nice frame with an explicitly computable dual frame so that can write every density matrix as a linear combination of non-negative terms.
Okay.
This is very much the spirit here. I just choose to not present it in this fashion.
All right. Yeah, thank you.
Can you try also another interpretation and tell if it's right or wrong or whatever? If we come back to the one qubit situation, you could rephrase in the same way we were there, saying that these red, instead of this red gas that is a convex combination of physical states, you would be using unphysical quasi-states to get it as a convex combination of oversized estimators. But now we're getting something even better in the other situation, that by using these for each of them uncorrelated, you are approaching the correlated row.
Yes, exactly. Thank you very much. And let me emphasize this. I'm perfectly aware that this is not an optimal single qubit estimation technique. You can do much smarter things. But what is not so easy is to come up with a method that naturally scales. And here, you could do 100,000 qubits, no problem. Because your estimators are elementary tensor products of 100,000 simple guys. You can easily store that. And then afterwards use this uncorrelated nature to really compute things very efficiently. And I think this is the main thing here. And thank you for also emphasizing this. Yes, Claudia?
And now I want to go back to Steve's question that can't you get unphysical states in this setting anyway from finite statistics?
Yes, I always do. I don't care about physicality.
No, I don't mean the final rule that you get. The final rule.
Okay.
The final expected
Yes.
value of this should be a physical, you want to estimate your rule.
Yes, but I outsource the question whether the original object is physical to begin with to the assumption that I prepared it on a quantum computer.
Yes. But then, like, okay, but you want to estimate that, and then you get some data,
Yes.
which you can very measure,
Yes.
and maybe this data does not correspond to any physical rules.
Well, this is why we need proofs, and we will do that next.
Okay, but finite statistics,
Yes.
it could happen that you
Yeah, it will happen, and we will do proofs to just address the final statistic case,
Okay.
which is the trustworthiness of the protocol. We're getting there. Okay, Klaus here raised an important point. The million-dollar question here is how many Monte Carlo samples do I need in order to get something reasonable and not completely crazy and physical, right? We now kind of like have an approach. Let's analyze how expensive it is. And this is what they do in the prediction phase. And spoiler, I kind of like shared all the necessary proof techniques for that with you already on Monday. You just didn't realize it. So we'll kind of like use our intuition from Monday in this new project to see that convergence happens much quicker than you would expect. But here, I now have to tell you how to make predictions. In the data acquisition phase, and we had a great discussion about that, we prepare these unphysical tensor products that are Monte Carlo approximations in the sense that they are simple, IID, so they are all independent from each other because they come from different experiments, and they approximate the true density matrix, whatever it is in expectation. Now, today I want to focus on the task of predicting linear functions, linear observables. We will do polynomials on Friday. You can also do it. Today it's linear observables, tracing a product with observables. And then I just use my samples and make these Monte Carlo approximation techniques, much like in the coin toss for the value of pi. I know that each of these guys gives me the right row in expectation, and so I form an empirical average. I average the observable value I would get for each of these guys for all different things in the typical Monte Carlo fashion, with the assumption that this will converge to the expectation value that I can then pull in, and then we will see that we actually approximate the right observable. But then we do that for all L observables in parallel. This is something that Monte Carlo gives you. And maybe a glimpse, Klaus, here for hope, is that in this setting, each of these observables is just a random number. So it doesn't see the underlying Hilbert space dimension. We are now really in a basic Monte Carlo functional approach where we approximate one-dimensional objects. Just many of them in parallel. This is not a density matrix estimation problem anymore. It's L different linear functions. And we can do that in parallel. And we can do that in a streaming fashion, meaning that we can construct these estimators while the experiment is running. If I want to do that with Steve's hardware, I would set up a computer with all these observables, and he would give me clicks. I would convert them into Monte Carlo approximations and use them immediately in all these observables. And when he gives me a second click, I update all of them. So there is no loss between data acquisition and prediction. And each estimation is now, and this is the important part, an empirical average. So 1 over m times a sum that is independent of random numbers, not random matrices. These random numbers don't see the underlying dimension. And now, here's the main result. That maybe gives me confidence, and maybe Klaus, you can tell me afterwards if it gives you confidence as well. But here is fix an arbitrary n-qubit state row. And now, in order to make the proof work, I have to assume that these observables have some locality structure, so that they are not super crazy global, but that they are maybe confined to omega many qubits. A bit similar to the case that we looked at on Monday. Then we can prove that the number of Monte Carlo samples you need to epsilon approximate all these target values in parallel with the same Monte Carlo data scales exactly the same way that we saw last time on Monday. It is logarithmic in the number of observables you want to predict. It is completely independent of the number of qubits. Let me emphasize that. If it's 100,000 qubits, the 100,000 won't enter there. The price we pay, and I will talk about potential improvements, is that we have this exponential scaling in the locality of all observables. This is what limits us. But there is alternative approaches that don't have this issue. And I really want to emphasize that the sampling process, how to generate the randomness, is easy. You prepare your quantum state, you do single qubit rotations, and you measure. And the storage of these individual Monte Carlo approximations is also cheap, because it's elementary tensor products. If you do it smartly, you can get by with 3 times n bits. For 100,000 qubits, that's 3 times 100,000 bits. It's not 3 to the 100,000 bits. Big difference. And the post-processing is efficient, because again, we have this tensor product.
So maybe you were going to talk about that, but before you had a 3 there that came from like maybe the oldies, but now you have a 4. Are you going to explain where there is a 4?
Well, not really. The 4 comes from the fact that we now have general observables, and so they are a bit richer and a bit more difficult than just Pauli observables. So for Pauli observables, you can get a 3 here. For general observables, you get a 4. We think it should be a 3, but we couldn't prove it.
Okay.
Thank you. Very attentive. I think, because I'm running out of time, I will do the proof of this on Friday. And will now kind of show you how these ideas really work in practice in the lab. Okay? So, Klausia, please be patient. We will do a complete proof sketch on Friday. For now, let me just show you how these ideas work in a real lab. And in our case, I'm Austrian, it was, of course, a trapped ion quantum computer for me. And here is kind of like what we did. Our friends in Innsbruck prepared an 8-qubit GHZ state, just as a target state, as a proof of principle. So this is not a very big problem, it's 8 qubits. And they did exactly kind of like what I told you. They prepared the 8-qubit GHZ state, then they did local random rotations, then they got the bit strings, and then we constructed Monte Carlo approximations, Monte Carlo estimators. And we used these Monte Carlo estimators to directly compute the fidelity with the GHZ state. So this is typically the target fidelity of like how good is the state preparation. And it's really just you take your tensor product Monte Carlo approximations, compute the GHZ fidelity for every one of them, and then you average. And what we also did there is we estimated a couple of entropies, a couple of nonlinear functions, which you can also do with this Monte Carlo framework. I will show you more on Friday. For example, we estimated the purity by just computing the purity of our Monte Carlo approximations. This is kind of like a trick that you can do. And if you know how to Monte Carlo approximate purities, you can also Monte Carlo approximate subsystem entropies, like subsystem ready entropies. These are approximations of the entanglement entropy. And we did all of that in a streaming fashion in parallel. Kind of like the experimentalist took data and the computer immediately built these Monte Carlo approximations and then made an ansatz for this, which he updated, and used the same data to make an ansatz for this, which he updated, and you took the same data to make an ansatz for all possible range entropies. There's a lot of them. Okay? In particular, subsystem or entropies of subsystems of size 2. There's a lot of subsets of subsystems of size 2 in an 8-qubit system. So this was in total dozens of different approximations, all fueled by a single experiment that provides clicks. We compute the Monte Carlo approximations and we update all of them. And here you can see a real-time evolution of all these estimators. This is really working while the experiment is running, and you can see the blue line is the important one, that fidelity kind of like quickly converges. You can see, the purity kind of like converges here, fidelity converges here after 11,000 seconds, and the subsystem ready entropies converge almost immediately. This is not a surprise, because the subsystem ready entropies are 2 local, whereas fidelity and purity are global objects are 8 local, so they need more data. What I really want to highlight here is that the convergence time for all these things in parallel was 60 minutes. And Innsbruck did a famous 8-qubit GHZ preparation experiment, maybe you remember that, a couple of years ago. They did physical quantum state tomography, they measured 24 hours and fried their computers for a week. So you can really see that this makes a difference. And to drive this home, I would ask the technician to now play the video. Video, please. So I'm now showing you kind of like a video that the PhD student did in real time for a 5-qubit variant of the same experiment. And you can see that kind of like all the estimators are updated in parallel, and you can see how they all converge. And it's not the coolest video, no special effects. And unfortunately, he also always pooled 500 shots together. So this is not a single data point, but it's already, I think, 100 data points or so. But this is really in real time. Fernando told us that ion trap computers are not the fastest computers, but it's working behind right now. It's generating data, and these are kind of like just a visualization of a parallel estimation of fidelity, purity, and all possible bipartitions. And if you just look at it, the bipartitions have already converged. On an ion trap computer after approximately 15 or 20 seconds. And this is, let me emphasize this is not difficult to do. The PhD student did it, I think, in MATLAB, as you can see. And like, this is something that all of you could also do. It's really not that difficult. And I think it's exciting because you can really see convergence while the experiment is running. And it also tells you when you maybe can stop. Because here you can see that these estimators have already all converged. You don't need more data. Here you see that the fidelity is also normalizing very quickly. And here, with the purity, which is a difficult object to estimate, we know that it is exponentially costly. You see that it really kind of like needs a bit more.
Can you comment on the first stage where we have purity more than 1?
Oh yeah, because I sacrificed physicality. I was very open about this. Kind of like all my state approximations are unphysical to ensure that they will converge here to the right thing. But I don't want to introduce a bias, because if I have few shots, biases destroy kind of like the physics. They do more harm than good. So just don't do that, and hope that physical convergence will happen quicker than you think. And the proof I skipped before actually shows that. That convergence can happen much more rapidly than what you would naively expect.
Just a question. For the updates, you're just using the usual Bayesian?
No. Just linear Monte Carlo updates. Nothing fancy.
Okay.
Like the experimentalist.
New data, calculate new average using the Monte Carlo.
Yeah, but calculating the new average is a fancy word for saying adding one number and renormalizing. Right? An average is a sum up to a normalization factor that I can easily update. I start with the first guy, take data, it's just a shot, I convert it into an elementary tensor product, rotate it into the right basis, compute all these guys. Time step 1. Time step 2, a second bit string comes in with a description of the basis I did. I convert it again in this elementary tensor product, compute all the things in parallel, and now for each of these trajectories, I had one data point before, I now add the new one and divide by 2. Third step, same thing. And then I multiply by 2 times 3 to like turn the 1/2 to 1/3. This is really, really quick. And now I think we've converged. Yes.
I don't know if I missed something, but what is the difference between the Lin, Inv, and the shadows?
Oh, ignore that.
Ignore that for now? Okay.
Ignore the yellow line. Good question. The blue line is what matters. We did like an alternative approach, which is physical, as you can see here. And here you can actually see that if you do something physical, it often happens that you have kind of like a bias and you never close the gap. But like our guy doesn't have a bias, and so we converge in the end. So this is another advantage of maybe not using physical estimators. And now my last joke, at the cost of Innsbruck people, I hope you believe me that this is data from an actual experiment, because if I, as a theorist, were to fake it, I would take a fidelity that is larger than 0.6. So they on purpose didn't try to do a good job in the GHG state preparation to really drive home the point that this estimation technique is doing very quickly what it's supposed to do. And with that, maybe we can go back to the slides.
If you just one question, like you have a theoretical guarantee of how fast you're going to converge, but you said that in practice you converge faster.
Yes.
How much faster? Like 2, 3 times, 10 times?
No, I think like factor 10, maybe even better.
Okay.
Kind of like these rigorous theory results we will do on Friday. They're kind of like non-asymptotic, so they're like kind of like no optimal to begin with, but the actual fact we pay typically a constant. But in practice here we notice that the convergence can be really also orders of magnitude better than our theory suggests. So yeah, this is again kind of like what you've seen already. For 8 qubits, it takes a bit longer. But after 60 minutes, you're basically there and you're done as well. And with that, I've kind of done for today. And I want to stop with homework challenges that you can do. Like the most important homework challenge is really instructive, kind of like to prove this single qubit equation that is at the base of our Monte Carlo estimation technique. That if I do these randomized approximations, I get a depolarizing channel. And if you're interested in these things, and if I did a good job, maybe you want to learn more, and I can recommend a review article that we wrote. It's called the Randomized Measurement Toolbox, where we explain these ideas again. But, and I find this almost more exciting, is Pennylane. It's like a quantum company. They have their own quantum computing simulating framework on classical computers, and they did an excellent tutorial where they really use Markdown to explain how you would code that, and you can code it yourself. Or just like download it and play around with it, and then you will see how it works. And I really, if you're interested, just do it. They did an excellent job. And I think the only way to really understand and appreciate these things is to try them yourselves and see how fast and parallelizable and easy it actually is. Okay? With that, I'm done for today. And instead of a summary, I want to use kind of like my stage time here to advertise a good book by my friend Rafael Chavez.
You are my book agent now.
Yes.
Thank you.
I don't know if you know that, but Rafael was approached by I think one of the largest newspapers in Brazil to write an outreach book about quantum information and quantum computation for the Brazilian and Portuguese market. And he did that in a remarkable quick time while the pandemic was going in his garden, and he got excellent feedback by kind of like all the editors and science communicators. And maybe this is interesting for you, it's very hard for me, but it's in Portuguese. It's called Incerteza Quantica. My Portuñol tells me that incerteza either means incision or uncertainty. I'm not sure. So yes, I think this might be a good read for many of you, and maybe also something that helps you talk to your families or friends, kind of like maybe find new ways of how to explain why you're excited about things. And I will try to read it to remind myself why I am so excited about quantum technology. But as you saw, my Portuñol is pretty bad. For me, it will be hard.
So let's hope it sells well, that I can translate it to English.
Yes.
So it's a half price. Since we are doing marketing, I just checked it. It's half price now. So we'll see. Thanks.
Incerteza Quantica.
Well, let's thank my book agent, please. We still have time for one questions. Are there any?
For how many qubits do you think this approach would be the best?
Excellent questions, and let me start by a full confession. I think this approach is never the best. Kind of like I stopped looking for optimal solutions because they are typically hard and don't scale. So this, I think, in every concrete scenario you could think of, you could find a better solution by working hard yourself and trying a couple of servers. I think this is a very good and scalable solution that will help us in the near future. But I think it's never the best one. And it works very well if you're interested in kind of like many different localized features. And there I can see a future from up to 100,000 qubits no problem. The problem is when you want to go to global features like fidelities or like really kind of like different difficult topological properties that maybe have a large correlation length, then these localized ansätze become expensive. Because you try to approximate non-local features with local approximations, and this can become expensive. But we will see on Friday that there's exciting takes on this setup where you don't do randomized single qubit unitaries, but maybe larger unitaries here, or maybe even a short random circuit, and there are very, very promising results that these kind of things still remain tractable and yield much better results. So this, I think, will really help us in the next 5 to 10 years, but there's also rigorous no-go results that tell us that they cannot be the solution to everything. I'm going to talk about that on Friday as well.
So, if I understand correctly, it's just n 1 qubit gates, right?
Yes.
Could you do the same, not for a global unitary, but like in 2 qubit gates?
Yes.
Two.
Yes, and all you have to do is to do the homework for the 2 qubit gates.
Okay.
And then you just retrace the steps, and you will get your own Monte Carlo estimation techniques for 2 qubit gates. And they will be slightly better for non-local properties and slightly worse for local properties. Excellent question. And a special homework for you.
Yeah, so homework, you will not announce that homeworks can become prize or whatever.
We can, yeah. So there is some cachaça available for those who have good solutions to give homeworks in the school. So they're just waiting for your solutions in this room. And well, so should we announce about the roundtable later? Yeah, so we are going to do some formulary that you can send questions. Like we are going to have this panel discussion. We call it lectures. At the end of the day, I don't remember the time. But yeah, so it would be great if you could give us feedback on questions, like things that you would like the lecturers to discuss and address. And so please send questions, and the best ones are going to be acknowledged with some little cachaças from the event.
What type of questions? Can it be like professional questions or?
Sure, like about career, anything.
Anything.
Yeah.
Should even be professional. It's not forbidden to have professional questions.
Ah, okay. Taking the reins is good.
I mean, things that you'd like to know about them, like
It's not only about cachaça. I think we have some toilets.
All right.
Also, that will be included.
Yeah, maybe. Right, there are some shirts also. And Steve, I think you also have some runningness thing, or? Okay. You want to announce that?
No.
Okay, great. So there are some
Not announced.
there are some surprises here. Okay, cool. So let's thank Fisher, then we'll go for coffee.